Hi. In this video I'm going to show you the metallic mean way to look at probabilities, and I'm also going to demonstrate how the hypotenuse lines up with the parent's finite boundary. And then I'll do a little bit of art at the end. Suppose a statement is false 9 out of 10 times. How many times should the statement be made so that there's an over 50% chance the statement has been true one time? So P is 9, Q is 10, 9 out of 10 times. And then S, which is the scale symmetry that we're using, is P over Q, 90%. D squared is the diagonal squared, W width, H is height. This is Pythagorean theorem. The width is 2 times P times Q. And the height is the width divided by the scale symmetry minus the width times the scale symmetry divided by 2. And the scale symmetry is also the diagonal minus the height, and all that divided by the width. Now this uppercase H is the vertical that defines the probability, 100% probability plane. We'll look at that in more detail in a couple minutes. So now jumping into Wolfram, I've already inputted the formulas. So now P is 9 here, and Q is 10. Doing the calculations. We see everything here is rational, so we've got a Pythagorean triple on our hands. Copying the information, and now putting it into Inkscape. All right, we've got what we need to answer the question with tiling geometry. So, first making the rectangle for the width and the height. So the height is 19 and the width is 180. And then doubling it, because this metallic mean way of looking at it uses 2 of the height, making the right triangle that defines the D diagonal, and doubling it up. So here we have our base unit, our base tiling, the 0th power child. Now we're going to make the 100% or 1 probability tile. So H is that uppercase H there, and W is just the normal width. So there you go, the uppercase H, 162. So now we've got all of the probabilities possible in this tile, and the child unit header above it in the 0th degree. And labeling the probability tile here. So the question wants to know when do we reach 1/2? And taking this 100% probability tile, dividing it by 2, now we've got 1/2 of that, or the 50% probability tile. So giving it the right label and making it a bit transparent, changing its color so it's easier to see the difference between the two tiles. Giving the base unit child transparency as well, so we can see how it relates to the tiles behind it. So now let's see how that uppercase H, the 162 height, relates to the D diagonal. Taking that triangle and finding its radians, arctan 19 divided by 180. So height divided by width, and we get 0.105 roundabout radians. Copying it for reference. Now using it to flip this right triangle. All right, giving it the right rotation and now putting it vertical, lining it up. So that's the length of D now vertical, and flipping around H so we can see how it relates. Yeah. Uppercase H is indeed D minus lowercase h, or 162. Which is 181 minus 19. All right, so I'm then taking the child and putting it to the first power to start to whittle down the probability tile to see how long it takes for us to reach 1/2 of that probability tile. So the scale symmetry constant is 9/10, and all we do is multiply this child by 9/10 and then tile it and repeat until we reach the 1/2 probability tile. Okay, so now we have child 3, the third exponent. This gets us child 4, the fourth exponent. Pardon me, we had child 2 and then we went to child 3. So now we're into child 4. All right, still not to 50% yet. At child 5. Getting closer, but not quite there. At child 6. Oh, really close. Let's see if child 7 does it. And yes, it does. It now goes past the 1/2 probability tile. So labeling these, starting with 0 and then child 1, 2, 3, 4, 5, 6, and finally 7. So we've answered our question. The answer is takes 7 exponents to get past 50%. Let's bring the question down here so we can see it. And let's add the answer. When the statement is made 7 times, there's an over 50% chance that the statement has been true 1 time. In other words, a streak of false has an over 50% chance of failing at the 7th instance. So now putting this into Wolfram to see if we're right. So 90% to the 6 and 90% to the 7. And yeah, that's when the transition happens from over 1/2 to under 1/2. So we did that with tiling geometry by using the appropriate rectangle's scale symmetry. Now, since 7 is in the vertical direction, we flip this probability tile so it lines up that way. There we go. So now moving on to some art, just for fun. Well, actually, there's some practical aspect to this. Namely, that even though we counted up to 7 exponents, this 100% probability tile contains infinite iterations if we wanted to. So by taking now another 8 tiles, 7 tiles, there we go, 7. No, that's 8. Let's then shrink it to the 8th power. Move that over, it'll look nicer. And here we are, we're up to 16 instances of, if we remember, each of these triangles is a statements. Add even more. And as you can see, the powers relate to how many tiles we have. We just keep on going. As many instances as we want. And of course, this relates to a lower and lower and lower likelihood of having only a false streak. So by the time we get down here, this little exposed remainder in the probability tile is hardly any chance whatsoever. You can barely see it. Just for good measure, doing it one more time. There we go. The likelihood of only false is so small we can't even see it from this height. Now, copying this for the art. We can see that a vanishing point has formed right there in the middle. So it's like the end of the tunnel. Alright, well, thank you for watching this video. Please post any questions or comments you might have below. I hope you enjoyed it and learned something. I have a few other videos that explain the system in a little more detail, and I'll come out with more and more. I also have some merch here that I've just started out. I'll show it to you. Here it is. I only have one right now, but definitely leave some comments below about your thoughts on my merch, and if you want to purchase some, that'd be a fantastic way to support my research. So here are some examples of different items with the merch on it. Cheers.